If you ever used ICs in your projects, then you might have noticed that most of them contain a triangularly shaped component in their simplified schematic. Those triangles are called operational amplifiers, also known as OpAmps. And since they are very common and useful for analog and digital electronics, I have used them before in a couple of different projects. So in this video I will show you what OpAmps are capable of doing and how to handle them properly. Let's get started. First off, you can get OpAmp ICs in a dual inline package with either 14 pins that usually features 4 OpAmps inside, or 8 pins that features 2 or only 1 OpAmp inside. As an example, I will use the popular LM358 dual OpAmp whose ground pin I connected to 0 volts and V plus pin to 12 volts, which is fine because it does not exceed the single supply range of the IC. Next, I apply the voltage of plus 1 volts to the plus inputs, aka the non-inverting input of the OpAmp, as well as a 10 kilo ohm pull-down resistor to set the reference voltage to ground. Then I created a voltage divider consisting of a 5.1 kilo ohm and a 1 kilo ohm resistor in this constellation between the output pin and the negative inputs, aka the inverting inputs. As a result, I received a voltage of 6.1 volts at the output, which equals an amplification factor of 6.1. But why? Well, the first golden rule of OpAmps gives us the answer. The output of an OpAmp will always attempt everything to keep the voltage difference between the inputs at 0 volts. That means there needs to be the same voltage drop across R1 as the input voltage Vin. If we now add the voltage divider formula to this and the fact that the gain is the output voltage divided by the input voltage, we finally get the classical formula for the gain of a non-inverting OpAmp. Such a circuit can be used to amplify the signal from a sensor, like for example a PT100 temperature sensor, or the AC signal from an electret microphone. This one creates maximum voltage peaks of around 100 mV AC, which I can now easily amplify with a gain of 48 by changing the 5.1 kilo ohm resistor to 47 kilo ohm. But when we observe the outputs, we notice another problem. Only the positive AC voltage got amplified, because the output voltage swing is limited to the supply voltage. That means we would need positive and negative 12 volts to successfully amplify the complete AC signal, which I can demonstrate with my lab bench power supply. But since that is normally not an option, we could also add a DC offset to the plus inputs. This way the complete amplification does work to some extent, but because we are amplifying a DC voltage as well this time, we hit the 10.8 volt output limit of the OpAmp pretty quickly. Why 10.8 volts instead of the 12 volts of the supply voltage? Well, there is no perfect OpAmp. The ideal one would also have an infinite high input impedance and thus no input current could flow, which is not true. It would have an output impedance of 0, which means we could draw as much current as we want, which is not true, and the list goes on and on. But on the other hand, there does exist rail-to-rail OpAmps that can achieve an output voltage which equals their supply voltage. And as long as you don't want to create precision circuits, such non-ideal parameters do not matter that much. But let's get back to the microphone amplifier. A more suitable circuit for this task would be an inverting OpAmp. In this constellation, the plus input is connected to ground, which means the minus inputs must have a voltage potential of 0 volts as well. And since the second golden rule of OpAmps says that the input draws no current, the current through R1 must be the same as through R2. This results in the classical formula for the inverting OpAmp circuits. And by connecting the plus input to a DC offset voltage instead of ground, we can amplify the microphone AC signal completely without amplifying any DC voltage. The output signal can then be connected to a speaker, but just like I said before, because of the small maximum output current, the sound is almost unhearable. The last important rule when working with OpAmps is that when no feedback is attached between the outputs and inputs, the output will either jump up to the maximum output voltage when the plus input has a higher voltage than the minus inputs, or in reverse, the output will jump down to the minimum output voltage when the minus input has a higher voltage than the plus input. The reason is the high open loop gain of the OpAmp, and such a configuration is called a comparator. And there also exist separate comparator ICs that achieve a faster response time than the average OpAmp. And with those 3 golden rules in mind, you can understand and build constant current sources and loads, voltage followers, integrators, differentiators, inverting, non-inverting, difference and summing amplifiers, Schmitt triggers, and the list goes on and on. As you can see, it is a versatile component and there's much more to say about it than what I just presented. But that is a subject for another video. Until then, don't forget to like, share and subscribe. Consider supporting me through Patreon to keep such videos coming. Stay creative and I will see you next time.